Consider a high-stakes medical diagnostic scenario. An artificial intelligence system, trained to detect microscopic lung nodules, scans through hundreds of CT slices in seconds. The algorithm operates with mathematical precision, identifying its target with 99.9% confidence. It executes its designated search task exactly as programmed. Yet, in many cases, it ignores a massive anomaly sitting right next to the nodule, the distinct silhouette of a gorilla, embedded directly in the lung tissue. Practitioners often assume that because an autonomous system can catch microscopic details human eyes miss, it will flag large, obvious anomalies. But this research reveals a deeper truth. AI systems do not cure human inattentional blindness. They inherit our blind spots, hard-code them at scale, and actively degrade the human vigilance designed to oversee them. This structural flaw extends to homeland security, defense, and emergency management, where artificial intelligence is increasingly responsible for primary threat detection. Human operators in these environments are now forced to rely on autonomous triage to manage a scale of data that exceeds their biological capacity. The objective of this breakdown is to trace how human cognitive filtering is converted into code, creating a persistent structural vulnerability. This vulnerability maps directly onto the architecture of modern autonomous warfare and security, where the ability to detect the unexpected is the primary mission. To understand the machine's failure, we must first look at our own. The human brain manages sensory overload by ruthlessly prioritizing specific search tasks and filtering out all other data. This eye-tracking data from a 2013 Harvard study shows that professional expertise can actually reinforce this blindness. Radiologists fixated directly on the image of a gorilla, but because their training was calibrated to find small nodules, their brains never registered the massive anomaly. This psychological phenomenon translates directly to physical security environments. In high-volume security lanes, threats rarely appear. This creates the low prevalence effect, an environment where the human brain's attentional thresholds progressively recalibrate, making screeners statistically more likely to miss rare targets over the course of a single shift. Expert blindness is not a failure of individual competence. It is an inherent property of how biological brains allocate attention toward expected patterns. Machine learning systems operate under a parallel limitation. They are interpolation engines, strictly bound by the mathematical parameters of their training data. This 3D scatterplot is an AI's training manifold, categorizing known threats by clustering data tightly inside a mathematical boundary. When a novel threat appears, it lands completely outside this distribution. The system has no mathematical vectors connecting its logic to the new anomaly. Studies from MIT and Nature Digital Medicine confirm that AI models inherit the specific attentional biases of the humans who originally labeled the data used to build them. While a human operator retains the capacity for surprise, an AI system is mathematically incapable of it. An out-of-distribution threat simply falls outside its reality. This algorithmic reality poses a challenge for initiatives like Replicator, which aim to field thousands of autonomous drones simultaneously. When an entire swarm shares the same algorithmic architecture and training data, they exhibit perfectly correlated blindness. If a novel threat falls outside the distribution for one drone, it is simultaneously invisible to every other drone in the formation. We have seen this structure fail before in human organizations. The 9/11 Commission identified a failure to connect the dots, precisely because multiple agencies shared identical institutional blind spots, all focused on the same historical threat types. Uniformly deploying identical models across a network replicates the same blind spot at every node in the system simultaneously. Defensive planning assumes that keeping a human in the loop, as in the Collaborative Combat Aircraft program, mitigates this risk. However, data from Horowitz and Kahn shows that human trust in algorithms creates automation bias. As systems perform reliably, human operators begin to defer to the machine, even when their own observations suggest an error. This graph illustrates the complacency spiral. Because the system is usually right, the human brain gradually stops actively searching for anomalies, and the cognitive skills required for oversight begin to atrophy. In rapid decision environments like JADC2, human operators are reduced to passive approval nodes, lacking the time or cognitive orientation to interrogate the system's logic. The automation paradox turns AI into a catalyst for human blindness, effectively removing the final line of defense against the unexpected. Operational reality dictates that the most dangerous threats will likely be out of distribution. One structural solution is the abandonment of monolithic AI in favor of diversified algorithmic ensembles. By using multiple models trained on different datasets and architectures, organizations can generate a broader perceptual field. Diversifying the algorithms breaks the curse of perfectly correlated blindness, ensuring that one system's blind spot is covered by another's unique perspective. Interfaces must also utilize frameworks like Safe AI to provide Level 3 situational awareness. This requires the system to proactively identify areas where its confidence is low, signaling to the human operator that the data falls outside its trained reality. Future security architectures must be designed not just to output confident detections, but to signal the exact boundaries of their own perceptual limits. No technical update can fully replace a culture of vigilance. High-reliability organizations prioritize a reluctance to simplify interpretations. This involves structured skepticism and adversarial red teaming. By formally assigning teams to search for what the primary system missed, organizations force the mandatory cognitive resets necessary to break the cycle of blindness. The catastrophic stale of Hurricane Katrina serves as a testament to unchecked normalcy bias. When organizations trust historical models over unfolding anomalies, they become structurally incapable of seeing the disaster approaching. True resilience requires moving beyond passive monitoring. Human operators must maintain active engagement with raw data to sustain contextual reasoning skills that AI cannot replicate. The gorilla remains in the room, regardless of who is looking for it. The only true defense is a hybrid architecture that is structurally designed to constantly search for the boundaries of its own blindness.